Hello again. We're going to determine an expression for the mass moment of inertia of a solid, right, or circular cone when rotated about its central polar axis. The cone can be defined as a body of revolution about the x-axis. It has a length from base to apex of h, a base radius of r, and a material density of raw mass per unit volume. Therefore, let's draw this. That's the y-axis and the x. The cone will be here. And it's rotating whichever direction from here to here. It's h. From here to here. It's r. Remember? This can be, it's a straight line, therefore y is equals to a gradient times x times plus c, and we know c is 0 since the y-intercept here is 0. What is the gradient? Its gradient will be change of y over change of r, change of x. Change of y is nothing but because here it's r minus 0, then h minus 0. That means the gradient is r over h times x plus c. C is 0, 2. And let's cut a disk here. This disk from here to here, it means its radius it's y. Its radius is y. What about its height? Is nothing but change of x dx. Change of x. And we know the density is equals to mass over volume, which is equals to mass over, what is the volume of a cone? It's 1/3 pi radius squared times its height. But now this cone is nothing but now this disk is nothing but now in form of a cylinder. That means its volume is going to be pi r squared times h. Is going to take this form. But now the volume of the disk will be change of the bigger volume equals to pi. What is the radius of the disk? It's y, pi y squared times the height. Its height is dx. Also, we know that mass is equals to density times volume. That means mass of the disk, it will be change of the bigger mass times density times now the volume. What is the volume? It's this one here, which is pi y squared dx. What about now the moment of inertia of a disk? Moment of the disk, it will be di equals to half the mass of the small disk y squared, which will be what? this is half. We know the mass of the small disk is rho pi y squared dx times now this y squared, which is height squared. We got that. Now what will be the moment of the cone? Okay, if we simplify this, it will be half rho pi y to the power 4 dx. What about now the moment of the cone? Moment of the cone now, it will be, because we have found the moment of the smaller disk that is cut from the cone, it will be integral from, remember, from 0 to h, because the cone is from 0 to h. So we integrate, because we want the moment of the whole cone, we integrate from 0 to h of the small cone. Now we use the small disk to come up with the equation, so that we extend it from 0 to h. Now this is integral between 0 and h. We know di, we have found di. Where is di? We integrate all this. Now integral of half rho pi y to the power 4 dx is equals to, we can take the constants out, rho pi between 0 and h y to the power 4 dx. But we know why. Let's replace y. Y is nothing but we know y from that equation. This is y here, r over hx. To the power 4 dx. We replace y with that y there from the equation, and this is 1 over 2 rho pi between 0 and h, r to the power 4 over h to the power 4 x to the power 4 dx. Now this is 1 over 2 times rho pi r to the power 4, h goes to the bottom, between 0 and h, x to the power 4 dx. We integrate this now. That means now we do have this will be equals to 1 over 2 rho pi r to the power 4, everything over 2 times what? 2 times h to the power 4. Integrate that, x to the power 5 over 5 between h and 0. This now, we substitute the limits, the whole thing becomes rho pi r to the power 4 h to the power 5 over 10 h to the power 4. H can simplify. We now have rho pi r to the power 4 h over 10. We know the density. Remember this density right here of the cone that we wrote here. We replace it. Now we have, which can be simplified as 3 m over pi r squared h times pi r to the power 4 h over 10. We simplify it because dividing by a fraction is like multiplying by the reciprocal. That's why the 3 comes on top right here. It's just simplification. And now the whole thing becomes 3m r squared over 10. Now, this is the moment of the code.